Hello and welcome to our physics class. Today we are going to see Young's observation. Young observed that when two monochromatic sources of light interfere each other, to get monochromatic source of light, we'll take two slits, two narrow openings, S1 and S2, and monochromatic source of light, a strong monochromatic source of light will apply on it. When the light rays will come out from the source, it will come out in the form of crest and trough. Solid line, suppose it is crest, and dotted line it is trough. Like this it is coming out. Then these two will become like a source of light. Here it will travel in the form of crest, trough, crest, trough. Like this it will travel in the forward direction. Then for the second source also the same way, crest, trough, crest, trough. Like this it will start to travel. Now what you observed was the positions where the crest overlaps and trough overlaps, dotted line, solid line, solid line, solid line, solid line, dotted line, where they overlap, there if you join, you saw that by keeping one screen at some distance, you saw that bright light is formed. But whenever crest of one wave coincides with trough of the other wave, this point, dotted line and solid line, dotted line and solid line, dotted line and solid line, where they intersect each other, he found to be dark. Like this, here also you can get it this way, crest trough, where they are overlapping crest trough, he found out to be dark. Like this, if you go on drawing crest trough like that, here you can see crest trough, then you get a bright light if you extend the screen. Like this, he found out a beautiful pattern on the screen. That means in the center, bright light is formed, then dark, then bright, then dark, then bright, like it goes on. Downside also the same, bright, dark, like that it will go on. It will look somewhat like your zebra crossing. Suppose this is bright, then it will look dark, then again bright, then again dark. Like this pattern was observed on the screen, and this pattern, bright light, dark light, bright light, dark light, we call it as fringes. We call it as fringes. And it was found out that the intensity of brightness in all the cases, they were equally bright, and darkness also they are equally dark. Like this it was observed. In the center it was a bright light. This is a B, suppose here. Then dark, again bright, again this side dark, this one also dark. Like this it was observed, and these fringes we call it as interference fringes. Now with this idea we can start doing his experiment. These two slits, S1 and S2, they are kept at a distance, say small d apart from each other. and this is a strong source of monochromatic light of single wavelength. Light rays, when it comes from this source S towards S1 and S2, these two S1 and S2, the narrow openings, we call them as slits, they will behave like a source of monochromatic light, or they will be coherent in nature because they are from the same source. Then he took one screen at a distance, say capital D, away from the slits. This is your screen. And these two light rays, they may come and meet each other at the center, at point O. They may come anywhere on the screen. So one point, we'll take it here as point P. At a distance Y from the center of the screen. And then we'll study his experiment now. This is your Young's double slit experiment. More popularly, we write it as YDSE in short. We'll start like this. Let S be a source of monochromatic light. Of wavelength lambda, say, two slits S1 and S2 are kept at a distance small d apart. The distance small d apart from each other. And then let d be the distance between the screen and the slits. Let d be the distance between the slits and the screen. Also let P be the point at which the two light waves interfere, and let P is taken the distance Y from the center of the screen. Also let P be a point, or P be any point on the screen at a distance Y from the center of the screen O. Like this, we'll write on the setup. Now, what you have to do here is, in this experiment, you have to find out the path difference. You can see the path difference, the path of S2 to P is longer and S1 to P it is shorter. So the path difference you can easily find out S2P minus S1P. The difference of these two distances will give you the path difference. Let us first find out the path difference. After you find out the path difference, then you will go to the relation that we did in the theory of interference, path difference and phase difference for constructive interference as well as for destructive interference. Then we'll get the positions from the center of the screen, at what distances from the center you'll get bright fringes, and at what distances you'll get dark fringes. Bright and dark, alternatively you'll get it. To find out the path difference will be your S2P minus S1P. Let us find out. We'll use geometry, or we can call it as Pythagoras Theorem. Then we can find out. At once you can write like this: S1P square minus S2P is larger, minus S1P square. These are hypotenuse of these two right triangles, S2P, then this point and this distance will form a right triangle. So when you say S2P square, this hypotenuse square is equal to base square, that is D square. D square plus perpendicular square. From here to here, this D, this is D by 2. This is D by 2. Because this distance is D. So this is D by 2. And this is Y. So it will be Y plus D by 2. It will be Y plus D by 2 whole square. Minus S1P square. Now this right triangle we have to take S1P square. Then this is again D square. And this distance will be Y minus D by 2. So D square minus Y minus D by 2 square. So here it will be plus. Then we will proceed ahead. This one if you open it, D square plus Y square plus D square by 4 plus 2 will get cancelled. YD will get minus is there, mind it. This is D square plus this one if you expand it, Y square plus D square by 4 minus 2YD by 2, it will be minus 2YD. But because of this minus, all the terms will become minus. This also will become minus, and this minus will become plus. Square plus minus you can cancel. Plus D square by 4 minus D square by 4 you can cancel. Ultimately you get 2YD. 2Y small letter D. Like this you will find out the difference between S2P square and S1P square. After this, you will use your algebraic identity. A square minus B square is A plus B into A minus B. This is equal to YD. Now here one small assumption. This S1P and S2P are nearly equal to D. You write down here like this. Since S2P is nearly equal to S1P is nearly equal to D, therefore this S2P plus S1P, if you do D plus D will become 2D. So we'll take like this. 2D, this one 2D, this is S2P minus S1P is equal to 2YD. So this S2P minus S1P is equal to 2YD divided by 2D. So this 2, if you cancel it, then you get the path difference. So our path difference, this is our path difference, delta x also you can write. The path difference between the two interfering waves is YD by D. After finding this path difference, now you go for constructive interference and destructive interference, at what points you get constructive and in which points you get destructive, that you can find out. Let us see. For constructive interference, that is for bright fringes, the relation for path difference it was n lambda. So your path difference n lambda is equal to yd by d. So from here you will get it. This is for constructive interference, the path difference, that will be equal to this one, yd by d. So from here you will get it, y is equal to n lambda d by d. So this will be your formula, the general formula, at which points you will get. And as you know here, n is equal to 0, 1, 2 and so on. So if you put the value of n, you will get the positions at which you will get bright fringes. Let us see. So first position y0, when this y0 for first bright fringe, y0 if you put, everything will become 0. That is y0 means it is at the center of the screen. You will get the first dark fringe. First the bright fringe at the center of the screen. So the displacement is showing 0. That means it is at the center of the screen. This y represents the displacement. Now let us see the second bright fringe where you get it. y1 is equal to 1 if you put lambda d by d. That is the second bright fringe. That means at this distance, lambda d by d, from the center of the screen you will get bright fringe. It's not only on upside, it will be downside as well. Equally it will be spaced, both up as well as down. Then y2, then will be 2 lambda d by d. y3, this will be the third bright fringe. So the position of the fringes, like it will go on y3, y4, y5 and so on for getting 4th, 5th, 6th bright fringes. It will depend upon the wavelength of light. It will depend upon the distance between the source and the screen, and it will depend upon the distance between the two slits. Actually this distance will be very small and this distance will be very, very large. The screen will have to place it very far from the source. Now the separation of the bright fringes to find out. And how much distance the bright fringes will be formed. They are equally spaced. Remember, all the fringes are equally spaced. The separation between the bright fringes to find out, you can subtract any two values, consecutive values. Suppose say y2 minus y1, it will give us the separation between two bright fringes. It is 2 lambda d by d minus lambda d by d. So 2 minus 1 is 1, we know, so it will be lambda d by d. They are equally spaced. They will give us the separation between the bright fringes. Now for dark fringes, for destructive interference, that is for dark fringes, we have the path difference that is 2n minus 1 lambda from the theory of interference. This is the path difference, lambda by 2. Then in our experiment we found out yd by d. So here you get the general form y is equal to 2n minus 1 lambda d divided by 2d. Like this you will get it. Now in general form we write this yn. Now for the first dark fringe, when n is equal to 1, here n value starts from n is equal to 1, 2, 3 and so on. So y1, it will be 1 if you put it. 2 into 1 is 2, minus 1 is 1. So it will be lambda d by 2d. This will be the position of first dark fringe. Here the distances are all measured from the center of the screen. Y, when you say this point y, P is a distance y from the center. Y and y1 means where the dark fringe will form from the center of the screen. That you come to know with this formula lambda d by 2d. And the second dark fringe you get it when you put n equal to 2. 2 to the 4 minus 1 is 3. 3 lambda d by 2d. This will be the position of second dark fringe. Like this you can find out y3, y4, wherever you will get the dark fringes. And here also the fringes, if it is bright, then next will be dark here, and at equal distance this side also will be dark. Again you will get bright, again dark, here also bright, again dark. Like that it will go on both the sides equally. So to find out the separation between the dark fringes, the separation between the dark fringes we will find out y2 minus y1. Here also the displacements y2 minus y1, higher order term minus lower order term you can do. You will get it 3 lambda d by d, 2d minus lambda d by 2d. So here you will get 2 lambda d by 2d. If you cancel it, it will be lambda d by d. It will be lambda d by d. So if you look this, the separation between the dark fringes and earlier we did the separation between the bright fringes, they are equally spaced. Both are lambda d by d. So this is sometimes asked in exam. Now let us see about the fringe width. It is the distance of separation between two consecutive dark fringe or two consecutive bright fringe. As we know that the distance between two consecutive bright as well as dark fringe, it is lambda d by d. So your fringe width will be also given by the same formula lambda d by d. Fringe width we write it as w. That will be lambda d by d. Now let us see about intensity of fringes. For bright fringe, as you know, cos phi must be equal to plus 1. So intensity, it will be maximum for bright fringe, that is I1 plus I2 plus 2 root I1 I2 cos phi. This was your formula. I1 plus I2 plus 2 root I1 I2 cos phi is equal to 1. As the intensity, you are taking coherent sources, here I1 will be equal to I2. Let us take it as I. Then it will be I plus 2 root I square. So it will become 2I plus 2I. It will become 4I. The bright fringes, they will have intensity 4I. Like that, you can do for dark fringes. For dark fringes, as we are saying that it is dark, cos phi, the minimum value is -1, so you will get I minima. And if you put in this formula I plus I plus 2 root I will be I square, cos phi is equal to -1. So you will get like this 2I, and plus into minus will become minus. This also will be 2I, so it will become 0. So this is how the minimum intensity you will get 0, and the maximum intensity it will be 4I. Now let us see graphically how we can represent the intensity of the fringes. The distribution of intensities. In Young's double slit experiment, the distribution of intensity you can show like this. This is your y-axis. The center, at the center of the screen, you know that you get a maximum bright fringe. You get a bright fringe. It will look like this. If you take in terms of path difference, this is lambda by 2, you get dark fringe. This is the position of bright fringe. And bright, this is dark. Here you get lambda. Then you get 3 lambda by 2. This is in terms of path difference. If you write in terms of phase difference, then this will be equal to pi, 2 pi, this will be 3 pi, and so on. This is your phase difference. So same way, similarly, this side will be minus lambda by 2, this side will be minus lambda, then this will be minus 3 lambda by 2 in terms of path difference, and here it will be 2 lambda, 2 pi, minus 2 pi, minus 3 pi, minus, here it is pi, minus 2 pi, minus 3 pi, and so on in terms of phase difference. Now here, if the light waves without interference, you can represent I, intensity of only one source, then it will be I. Then next phase you can represent like this. To here you will get 2I intensity without interference. And the topmost line, this is intensity with interference, you get 4i. It's intensity with interference. So from here you can even know that this y-axis represents intensity. Y-axis represents intensity. And this is for constructive interference. You get 4i, that is for bright fringes. And 0 you get for destructive interference. This is at the middle, at the x-axis it will coincide. So there will be no. These are the points of destructive interference, and these are the points of constructive interference. Now we shall learn about the relation between the width of the fringe. There exists a relation between intensity of the fringe then amplitude and width of the slit. These two you already know, relation between intensity and amplitude. Suppose two waves with intensity I1, I2, then they are directly proportional to the amplitude of their waves A1 A square by B square. That is also equal to the width of the slits W1 by W2. So we have to remember for solving the numericals. Now let us do one or two numericals based on interference. Let us solve this numerical and see. In Young's double slit experiment, the width of the fringe obtained with light of wavelength 6000 angstrom unit is 2 millimeter. So this is the width of the fringe. Now, what will be the fringe width if the entire apparatus is immersed in the liquid of refractive index 1.33? The whole apparatus, if it is immersed in a fluid with a refractive index 1.33. Fringe width in air, fringe width, let us say in air we did first. Let us take it as beta. Your formula is lambda d by d. Now, this beta value you know it is 2 mm, but I will put it afterwards. And fringe width 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 in the liquid, let us represent as a beta dash or beta 1, either way you can represent. Here if the light passes in the liquid of high refractive index than air, then the wavelength will change. The wavelength will change. Let us write this lambda dash d by d. Now these two ratio if you find out, like this will do beta dash, therefore beta dash by beta is equal to lambda dash d by d divided by lambda d by d. So ultimately if you cancel dd, this capital D also, if you cancel it, you get lambda dash divided by lambda. Now as we know that wavelength is inversely proportional to refractive index, so here it will be mu dash, that is for liquid, and here it will be for air, mu. Lambda is for air. Here we have taken lambda for air. So here the value will be, for air mu value is 1, for the liquid they have given 1.33. Then we'll take these two terms, beta dash by beta, and this is 1 by 1.33. Beta dash by beta, you know already it is 2 mm. is equal to, or first write down the formula clearly. Beta is equal to 1 by 1.33. So from here beta, you know the value, beta dash will be equal to beta divided by 1.33, and beta as you know it is 2 mm divided by 1.33. So 200 for this decimal, 2 digits, so 2 zeros I am putting, 133 mm, and I'm dividing, you get the fringe width in the liquid. 200 divided by 133, 1 time is 133, 10 minus 3 is 7, 9 minus 3 is 6, 0, then decimal will come 133, 5 times, let us see, 15, 16, 6, 1, and 5, 6, it's around 1.5. So you can write 1.5 millimeter. Like this you can find out the fringe width inside the liquid. The whole thing is immersed inside the liquid. And the next thing that we'll have to know is about conditions of sustained interference. Here, to obtain a well-defined observation pattern, we call it as conditions for sustained interference. The interference that will produce black, white like that, it must be well defined. Then we can say that the interference is sustained. You can study the interference pattern. For this, to obtain a well-defined sustained interference, we have some certain points to be remembered. Although some points already were doing Young's double slit experiment I have mentioned, will just be a repetition, but 1 or 2 points, new points will come out. The two sources producing interference must be coherent. The first point that we have already discussed. To undergo interference pattern, the two sources must be coherent. Then the second point, the two interfering waves must have the same plane of polarization. So if the two waves are already coherent sources, then they must be vibrating in the same plane. Now here polarization, if I say this is L, polarization, this topic is removed from your syllabus for this year, but polarization, little bit idea you should have. When we talk about electromagnetic wave, light is an electromagnetic wave. So there are two field vectors. One is electric field vector, it vibrates perpendicular to the magnetic field vector like this. The two are coming perpendicularly and reaching our eye. So among these two magnetic field vector and the electric field vector, if one of them you can remove it. To remove it, we use Polaroids. They are made of tourmaline crystal, or we can make artificially as well. So if one of the field vector is removed, the intensity becomes less. So that means one plane of vibration only must be present, either this one or it must be this one. So the two sources coming out from S1 and S2 must have only same plane of polarization to obtain sustained interference. Then the third point, this also I already said to you while doing the experiment, the two sources must be very close. Then we took it as D, small letter D. The distance between the two slits must be very close to each other, and the pattern must be observed at a larger distance to have sufficient width of the fringe. And the pattern must be observed at a larger distance. That means this capital D, the distance between the slits and the screen should be very large. Then you can have the sufficient width of the fringe width will be bigger. You can study them carefully or correctly. Then the fourth point, the sources must be monochromatic. This also we have discussed already. It should be of single color. Light should be of single color with same wavelength, or else otherwise the fringes of different colors will overlap. If you use polychromatic light of many colors, then the fringes, the colors will overlap and will not be distinct. You will not see the fringes distinctly. And lastly, the fifth point, the two waves must be having same amplitude. This one we have not discussed. The amplitude, the maximum displacement of the particle from the mean position, then we call it as amplitude. They must be of the same amplitude. For what? We require same amplitude for better contrast between bright and dark fringes. Dark will fully look dark, bright will be fully bright. The two must not overlap like this, bright and dark, then it will not be clear. So for that we require same amplitude. Light source must be of the same amplitude. These are the 5 conditions for obtaining a sustained interference. With this we have come to the end of this video about our interference. In the next video we'll discuss about diffraction of light. Thank you and have a nice day.